So, like we discussed in last lecture, that failure mode mechanism and this kind of thing, and we finally picked up the failure mode mechanism and effect analysis, because mechanisms are very important for POF. This particular strategy has been, and now we will see how it is applied to electronics along with the models and methods also. So, let us see. First step in POF approach is data collection. So, what are the sources of data that we are depending on? Because reliability assessment requires lifetime loads also. So, collecting the information becomes a critical part of, if the information is correct, our model will be giving right output. If information is not correct, then we might not end up with the desired results. What we do here, the product information is collected, and what is that information? Design specification, material, layout and dimension, and of course a quality attribute is associated with this, because that one single factor, quality, if there is no quality in this input, then there could be, or they are incomplete in the sense. For example, if I have not taken into account, if I am designing a system, what kind of error a human can make, how he can make turn the knob left or right by mistake, how a person can do some mistakes in calibration. Okay, even though they are all domain expert, but once in a while it happens. So what happens if the same oil is added in three parallel redundant system bearings? It will be common cause failure. So I would say whatever system we developed, if we want it to perform or to qualify as a safety system, then we should have follow the template of safety system, which includes not only specification, material, layout and all. There are many reliability metrics that it takes into account, because they are the human factor, and human as a common cause factor becomes very important. There are other aspects also that we need, but since the lecture is there, we have to take into account all the dimension. Not only that, we are developing at card level, some human card level reliability or something, or card level failure rate. So it has to be holistic to the extent possible. Then life cycle condition. So life cycle conditions are what? One is operational. Operational loads are like, suppose if there is a electronic card in a instrumentation rack, and that card has been designed mill grade. It is a mill grade card. So ground benign condition. Okay. So ground benign condition means temperature, humidity. That comes under the environmental condition. Okay, temperature, humidity and exposure to corrosive substances. And then when we talk about its operational parameter, current, voltage, its a mounting, its a connectors, and what kind of maintenance it is done in the operation, and whatever instruments we are using for maintenance, whether they are qualified, they are calibrated, and they are periodically validated and verified for a given application. If instrument is not proper, then operational issues will crop up. So typically, if we see what are the direct operation parameter, it is voltage, current and mechanical loads. Okay, but then suppose I have installed a card in an electronic rack, and if I do not see how the magnetic impulses or electromagnetic impulses, how it affects the card. So then I have to talk about all the safety and security of the, because security, apart from safety, security has become a new dimension to the card. Or suppose how some effect can be implemented, unwanted effect can be implemented. See, human error is basically it is referred to the random failure. Okay, humans are trained, highly trained actually. So, we know that randomness is a component of each and every field that we have over here. So we talk about, so we have to have operational environment and both the things together, and we have to life cycle loads, we have to operational environment we have to take, and then we have to designate how long this will be there in use. Then quality, as I mentioned, quality in product design and associated tolerances, limits, acceptable criteria, material characterization, testing, and specification along the project and reliability metrics, supply chain information, including shelf life and all that. Often the components are bought, and then it has got a storage life. Every component, when it is in storage, it should be requalified for use in the plant to avoid the unwanted scenarios. Customer expectation. This is very important, and I think if modern industry, if they are flourishing, it is because customers' concerns are taken into account. And then we come to a very important point, the gap areas. Gap areas in what? Whatever the product was expected to come out, and what is the customer expectation. Of course, when a product is developed, customer expectation will, but there has to be a survey. And from this survey, it should be ascertained what are the gap areas. So, ideally speaking, there should not be any gap area, because whatever information has come, to the extent possible we have met. But suppose if something or some matrix was left out, the company or the manufacturer, they should chase for this thing, and maybe in a couple of years or months you will get the feedback, and you will see the reality of this, whether we have to go for additional research and changes or modification, and maybe in a 2 or 3 years time the product will be fine for the market, because all the feedbacks are there, all the inputs are there with you, and we have tested it and we have modified the system. So that's how the physics of failure is a very important approach, and it should be part of any and every industry, because it is a science-based approach, and in long term it is going to handle even the complex problem easily, and especially for prognostics and health management. Now we have been talked about it. Some of the approaches we talked about, MIL 217. I think we have not talked about IEC 61508. In fact, this approach is compared to the other approaches. We are not comparing with the physics-based approach. It is most complete in the sense that it provides a indicator of safety integrity level. You know, what are the safety, and it is a probabilistic in nature also, because it talks about the frequency and what are the system that will need SIL system integrity level 1, 2, 3, 4 and all, and there are industries where overriding factors are safety only, like nuclear industry. So for this type of nuclear industry is a complex system that we know, and there, if their safety is an overriding factor, so this SIL to SIL or IEC 61508, this methodology is used extensively. Of course, MIL 217 plus also is used, but then these two together, they have a promise of giving better results. So that here we talked about the handbook approaches, and again let me repeat, when I talk about the handbook approaches, there are softwares that are available. They are facilitating these approaches, and very effectively we can use it actually. Then tabulation approaches, failure mode effect analysis. It looks check the what has failed, what were the mode of its failure, and what effect it caused. So that means there are 3 attributes here, and it is a sort of a brainstorming type thing, and we go on recording each, and whichever becomes sensitive or important thing, pick up from there and go for modification or responding to the or improving the situation. Okay, so this is one of the simplest approach that we have, and it has been going on, and it still works better for systems. But only limitation of all these approaches is they are work in isolation, in the sense that how it is connected in the plant in a complex system. There is a no clear-cut guidelines on that. So we do FMEA for a component, FMECA for we do for some mechanism. Of course, we list out the mechanisms and which mechanisms are important. We have in tabular form, and we have a risk ranking and all that, like criticality and all. So it becomes something like FMMECA. So it is there, but we cannot compare these methodologies with a probabilistic risk assessment system, wherein each and every component of the plant, ideally speaking, should become part of the final estimate, and especially safety systems. We should go to the extent of, so that kind of, but still most of the applications, they require dealing with a component specific criteria. So these approaches, they do well and all. It is here failure mode effect analysis, failure mechanism is important here. Here criticality, FMECA, criticality is important, and here we have diagnostics which are important. So these are the manifestation of, I would call, FMEA family approaches. Now probabilistic system approach. Probabilistic approaches are available in two, as we discussed there. Same as above we have there, but then it provides a system integrity level, and that we have discussed. And if we use a probabilistic risk assessment approach, where not only electronics, it can fault tree, event trees are the two cornerstone of probabilistic risk assessment. Then Markov and so many Bayesian and so many things comes into the picture. So we have this approach, and it is internationally, it has become very popular. Let it be nuclear domain. You talk about the space system. If you call, in fact, in defense system also there are increasing application we have here. So, but then often when you do PSA and there is some electronic device or card level, we have to fall back on this report, physics of failure and Milb handbook approach. So it's not that they are also used, but it is a small component of a big model that you created, where there were mechanical, electrical, electronics, and components, and there even civil components, and there we have this electronics which is at the core. Why? Because a production strategy is implemented by electronics. Okay, and if you talk about the power electronics, it is the power supply electronics which are critical areas, and that is how power electronics and microelectronics both are. Actually, I found there was no specific scope for developing the, showing you the electronic component. Like it's a PNP transistor, and it's got a base, collector, emitter. So input, output, and then you have, so PNP. When NPN is emitter, is the output, and base and collector. So, but then I have brought in, because we were in probabilistic domain and then AI/ML. So slowly I will be talking about the specific electronic. And one comment here is very important. Now we are driven by the transistors. Billions of transistors, millions of transistors on a controller or processor. Field programmable gate array is a special component over there, and you can design your circuit. You can embed the system over there instead of having components distributed across the card. You can embed as many card components as possible, and then the performance can be evaluated. And generally, this technology has been doing very well, except for one reason, that it has got a software sitting on the component, and that is limiting its application in safety critical industries. Okay, and there also with a redundant arrangement it is being used, but yes, it is being used in most of the fields, whether aviation, electronic, aviation, nuclear, process and chemical industry, any industry you talk about it. And we are depending heavily, even our laptops when we use, or even if our cell phone we use, we are having these transistors, billions of transistors sitting on there, and they are doing our job in 0 and 1 thing. Now, why FMEA for POF? Okay, first is it is a tabular approach. Okay, and we can list various mechanism and all, because now we have again come back to our POF boundary. POF is primarily component specific approach. Okay. So we can work on, so it is quite possible that in electronic board we identify the components which are resulting into unsafe failure. Suppose if my system is safety critical, so I'll find two, three components which are failing in unsafe mode, and I'll use this is what as a part of PRA we have done many times, that have those components and do, because if card fails in same manner, no issues, my plant will be shut down. Of course, that also should not happen, but safety comes before the performance. So that should, of course, safety also lead to plant unavailability. So that connotation has to be seen, that availability is because of process system failure or safety system failure. But we are talking about electronics here, and in safety system they have a lot of importance. So have those components which are very important and their unsafe failure, protect against the unsafe failure. So that is where again POF approach can be effectively utilized, because it is resource intensive and it cannot be applied to all the components. Okay. So two modules, model, mechanism, and link between the there are, see, mode and mechanism, they have a connection here. In my normal plant environment, what mode of failure and what is the mechanism? So that's why FMMEA, these are directly relevant to the plant. Major efforts in POF is dedicated to data collection, development of test metrics, and microstructural analysis. It is truly science-based approach in the sense that a complex simulation can only be done when we have data, when we have a model, and that model is correct, and then we demonstrate and validate that model, and then when we say, okay, now this approach can be used as part of prognostics and health management. Arriving degradation level, and finally this is also giving time to failure means what? It is remaining useful life, that is it can be interpreted there, which we say normally in PHM. Uncertainty, yes, it provides a opportunity to present the time to failure with uncertainty characterization. If uncertainty is larger, then it is not acceptable. Let us say, be very frank. If uncertainty is acceptable, because what will decide whether it is okay or not? So uncertainty is one of the metrics that will decide whether it is applicable, it can be used. Okay, so again I am trying to introduce some electronics. Again we are talking about MOSFET, metal oxide semiconductor field effect transistor. These are the very well used in the industry, and this is I am indicating the construction features. So normally these transistors are very small devices, semiconductor devices actually. So we know that transistors have one base, one collector and one emitter. Okay. So and both are all the three components which are connecting to the electrical circuit are aluminum. Then we have a field oxide. In fact, this particular area should be isolated. So there is a substrate, So it is sensitized to P level. There is hole level. Okay. And then this area is called depletion boundary, because the electron will flow out into this region, and here it is called channel. Drain contact, source contact, gate contact, typically we see in all our symbols actually. And then we have a substrate where this whole thing is sitting, and it has to be made in such a manner there is no leakage current. There is no leakage current, So that has to be, so leakage current is one of the failure mode or mechanism for a MOSFET actually. So, but MOSFET as a construction feature, it is typically it is used in electronics because function of I'll come to those kind of thing. Here let us understand the construction feature only. Now, what is that procedural steps are there in FMEA? So, life cycle of the product, that information we have to collect, okay, and that has to be as complete as possible. Any one factor missing, like if I am designing a component and if it is going in some country where the temperatures are going up to -30, -40, my electronic product will not perform there. So that means I have to take into account the location parameter also. If I see that there are some certain locations, they see the magnetic field effects. So my electronics should be validated, developed and validated for those kind of effects. Then there are some seashore. If I am putting some electronic component, the humidity is very high. So and humidity and temperature, these are the two enemies of electronics actually. Dust, of course, dust is also. So we have to take into account the life cycle of the product. Failure mechanism. What are the critical failure mechanism? Competing failure mechanism, because it is quite possible two failure mechanism can lead to the same failure modes. Okay, so that kind of study and depth of, in-depth database should be there with us. And cause and consequences of failure. The cause and consequences levels, they bring in the factor of importance of the procedural steps of the component. Okay, and then of course this identify the life cycle. What are the things? Define system and system elements and function to be analyzed. This is a very important thing. This defining itself takes a lot of time, and we have to define the failure criteria also, failure mode and failure criteria. Which are the modes are important to us, okay, and which are the failure mechanisms which will come later. Yeah, here causes and mechanisms that will be of interest to us, which safeguard my industry interest actually. Identify failure models, and this is the most serious and efforts, because it can be done only under lab environment, because we are developing failure model. All the knowledge that I have gathered there, it goes into the developing failure model. Number of iteration, number of testing, number of analysis that has to be done. And if it comes to the material characterization, that kind of separate tests that have to be done, going up to not only up to grain boundary, even beyond that, how over a period of time the material structure changes, and that's how we'll come to a model, and then prioritize the failure mechanism. So there could be more than 2 to 3 competing failure mechanisms, and we have to see which one, and that will get the highest priority. It's not that we will ignore other mechanism, but we'll take into account. But most of our modeling will be going on the competing, the most important. There is something called importance analysis in probabilistic analysis, and we have to do that kind of exercises. Okay. Then suppose if I told you those things on the chart, but suppose if the step number 1 is logical elements, that is at system level. What are the if I have a card, what are the different components making the card? And then the product or system whose reliability to be predicted is divided into logical levels. This is the first important job that we have to do. It's a location, it's a path, including metallization becomes part of it, and what is the proximity to the next component, because that will again determine performance of the electronics. Then failure criteria. Failure criteria can be worked out at the card level. Then if the card is working with some other system at that level, and then finally at the plant level, that means at the mega plant level. So all these failure criteria, they will be guiding thing what we have to do, which are the failure modes or criteria we have to work on this. So so all this architecture should be there with us, and then only we go to the breakdown of elements depends on the design and lowest level at which information about the very important thing is, if I divide my logical level, I have n number of things, but if I do not have details of this, what is the use of that? So you have to decide the level of your analysis, which level should be highest level, where the information is available. And if I have assumed certain things, then probably a sensitivity analysis is the critical exercise that can be done, or the experiment can be done to override those kind of issues. Then failure mode. Failure mode is the way how component fails and what are its effects. They become important because it affects the other system, it affects the complete system. So one levels of failure mode can be lower levels of failure mode. So failure mode also, if I go to, like suppose if I say that wall failed to open, a mechanical wall, it failed to open. Now why it failed to open? It is because of corrosion of the shaft, on the shaft, or some mug collection. Why that mug came? Now, other secondary thing, it will require a detailed analysis why it corroded. So we have gone into corrosion modeling. If I have a let us say diode, it is meant for, so there is some leakage current. How that leakage current occur? Because diodes are inherently made in such a way that reverse current should not happen. So if it start leakage current is happening, what are the substrate, what are the component wise those issues are there. Okay. So then the scope. What should be the scope of the failure mode exercise that we have, whether we are remaining at the component level or we are going at the board level, and even the investigation also is what is the level up to which we will go in microstructural analysis. Of course, the idea is to have an optimum scope so that we can deliver the best whatever was assigned in terms of failure mode. Now, there are some example. Failure modes are crack. Now, crack can happen because of any reason. It is because of stress consideration, it could be strain consideration, it could be in time domain, today 10 years, 15 years. So then voltage drop taking place, structural damage and spark. So what is our exercise, and we have to do high testing to ensure that that period is covered, and we have taken the worst case scenario for designing or performing that failure analysis. That promise should be there from our failure analysis. Life cycle conditions. So life cycle conditions are that obtained from profile, how it is going to operate. If it is a component is operating in a ship, it is saline environment. So maritime will have its own challenges. So a component has to be qualified in a different way. Of course, if a component which is not pretty, we have to do maintenance repeatedly, and then we have to be very particular about those aspects. Okay. Or we have to design the room where they are lying, where the humidity is ground benign conditions are maintained. Okay. Then major elements of life cycle profile are, the life cycle will include design phase, manufacturing phase, transportation, shelf cost, where component is in the industry, whether it is a dusty environment, whether humidity is high, whether temperature is high, or whether it is a dust environment, and what kind of maintenance and the safety culture of the plant that is there, because these things they affect the plant in a big way, and probably that can be part of our recommendation in which ecosystem the component should operate, or our promises for which system it is applicable. Critical information is life cycle this thing profile. So we have to give, and should be encompass the occurrence and duration of these conditions. Typical examples of LCPs are condition include loads such as temperature, humidity, pressure, vibration, and they are all known to everybody, but every industry has their own specific criteria. Okay. Accordingly, failure mode effect analysis should be done. Okay. So then assessment of failure root causes. Okay. That is related to mechanism only, because root cause analysis, if it is a serious issue, it forces the industry to go into the root of those failures so that such failure will not occur. So root cause analysis becomes very important there, and we have to identify their sources, and the example include typical failure of root cause include human error. Now we had what condition we laid out here. I have not got human error here, voltage current that we are talking about, but finally I am bothered about mode of component failure and its root causes. So I have to take, and then is it that this component is inducing failure of another component? That means this component has failed. It has generated some heat. Then my next component also has failed. So those kind of sensitivity should be built around these models and methods. Then failure mechanism, I think I have talked to you that failure mechanism is the central, and here and now I am directly referring to human error in the root, both fatigue and overstress, and this thing should be taken into account, the PCB. Then failure models. So there are many models that are available. Which model you will use? You can start. Probably you can plot your failure data, because whenever we do some study, we do population, put population under testing. If there is a diode, I will put 100 diode under test. If there is a relay, I will put 100 relays under test. So based on their failure mechanism, I can, the data if I plot, I can make out whether it is following exponential, power law, or linear distribution. So TF is time to failure. That is the parameter of my interest out of POFE, and this is some constant and this is some exponent, and that's how power law model. Exponential model is like again some constant, maybe process constant or material constant, and minus y and x are the parameter of the distribution. So now we talked failure modes, models, and this becomes the subject of our discussion because failure mechanisms we have to give failure model, and there are some models that are available especially in electronics, and a POF model relates to failure to time to failure actually, or loading condition or environmental condition or operational condition. Okay, so if I take the component like there is a component for failure location is a component. It could be board or metallization. You know metallization, the copper line, old electronic board running across the board, it is called metallization, or even it could be even interconnect. The solder joints and all they are, and then individual components, board metallization and interconnect. These are the three failure location that we have to talk about. If I have to talk about component level, time electric dielectric breakdown or hot carrier injection, this is a very prominent thing in electronics, and the failure model is exponential failure model, Notre Dame model, and power law model. You can see that what we are trying to say here is you can create your own failure model if you do experiment and if you collect the data. It could be accelerated test because it's not possible to put a component for 20 years test and all that. So we have to acceleration factor we have to use, and then these models we can come out. Electric field in the oxide, so temperature, you will see temperature is there in all and everyone. So and the current density, these are the something which are very important, peak current and appearing everywhere. Okay, and you can see stress migration for interconnect. Here only tensile stress and temperature stress. That means mechanical and thermal. These two parameters have an exponential model. This will be discussing in detail. Time, you have to remember time dependent dielectric breakdown, TDDB, hot carrier injection, HCI. Corrosion is one of the additional factor. For corrosion we provide passivation layer, so it is reduced that humidity or doesn't affect the board. So it is relative humidity and temperature. We have corrosion ironing model is there, current density and all those things are affected. There are some sources that we have used here for giving this information. And of course, now let us see, we talked about the electromigration. Electromigration involves due to high current or through these are metallization. You can assume these are the metallization on the board, So high current passing through the it and the atom gets dislodged. And over a period of time, this becomes a cavity here, and this becomes a bulging point at the point because atom dislodged from here and got deposited here. And sometime it so happens, this failure mechanism, this thing they get aligned and it happens shorting up metallization. So metallization interconnects on substrate. They are basically located on substrate, board material actually you can say. Okay, so time to failure model, it is got TIV is time to failure for electromigration. Rest you can read the phenomena I have explained. So we have time to failure P0. P0 is a process material dependent coefficient. Okay, and then J is current density. Okay, and current density is in the metallization here, and this is actual and critical current density. Actual minus critical density, and that will give us exponents n, and this is a Kb is a Boltzmann constant. Okay, A is activation value and T is the temperature in Kelvin actually. So it is a simple model which is available in open literature, and you can talk about the metallization in your electronic board. Maybe for many projects this can be one of the studies actually. And then time dependent dielectric breakdown. So the degradation involves the phenomena of leakage current. Why it is important? Because it leads to a leakage current, finally need a short circuit due to failure of the transistor gates. I showed you in my previous slide. Transistor gate, if they leach or they through substrate or so the dielectric breakdown, the degradation mechanisms involves creation of charge trap within the dielectric, diminishing the potential barrier, understanding the trap generation mechanism is key to evaluating oxide degradation. How oxide? Time dependent dielectric breakdown. Okay, and for the model for this is time for BD breakdown is equal to N into, it's a long formula, activation energy. So this is Boltzmann constant, temperature, and then we have some constant, okay, and voltage driven, and S is another coefficient we have here, and N is the ambient temperature pre-exponent value, okay, temperature pre-exponent value, okay, and like that this model has been built, and it is more complex than the electromigration, but yes, the and this is delta is activation energy. Hot carrier effect. Hot carrier effect is carriers refers to the electrons that travel from source to drain in a metal oxide semiconductor field effect transistors. It is specific to MOSFET actually. I showed you the diagram. So how the electron travel from source to drain, and this is a mechanism associated with the hot carrier effect. Attaining the kinetic energy due to the surrounding high electric field. So electron receives additional energy and they start moving and breaking through interfaces that are intended, such as dielectric. You saw there the dielectric, and forming interfacial status. So here for hot carrier effect, time to failure is P0 again is some constant, and then get current, and then W is some factor, is the width of the, sorry, not factor, width of the transistor, and then exponential, again the same term, A by Kt. K is Boltzmann constant, T is temperature, and then A is activation energy. So we saw three most important degradation mechanism for electronics failure. So what we saw from that sense, this lecture is very important because it has directly given you a peep into how the electronics degrade actually. Rest of the job is basically routine data collection, analysis and all, and creating a software for simulation and all that. There are professional softwares that are available, not in market, but with some labs. I'll come to that, those kind of things, which will enable you to perform virtual simulation also. So we have seen what is FMEA, procedural steps in FMEA actually. C part was not there. In fact, somewhere in the discussion I have seen in POF, criticality was also used. Why? Because we have a card, different component, we have to put, if somewhere the zone is crossing certain limits like signal or red, then you prioritize them, green lowest, red highest. So that kind of color coding can be done. Failure, and I will show you a software also which does that actually. Okay, failure mechanism in electronics component, time to failure model, electromigration, time dependent dielectric breakdown, hot carrier, that we have discussed. 40 will be discussing in the next lecture.